Hello. So this this is a NeurIPS review presentation. It's more on the general interest stuff. You don't need such a technical background or domain-specific knowledge like for the RL presentation. Yeah, some of this stuff I think is really interesting. So a fantastic thing that they're doing is they've got live stream videos. So I think all talks are live screened. You can watch them on Slides Live /NeurIPS. I actually watched a lot of the talks from home. And there's also meetups being organized in cities around the world, so you can watch these with other people and chat about them, even if you can't make it to Vancouver or wherever NeurIPS is being held in future years. One thing they are encouraging softly or gently is reproducibility. And so now 75% of papers have posted their code, up from 50% in 2018. And about 10% of papers are pure theory papers, so obviously they didn't have any code. So there's like 75% of a possible 90% now have their code up online, which is pretty awesome. Yeah, and their method is just have a checklist. And I don't think you need to you don't need to check everything off in order to be accepted, but this gentle encouragement seems to be making a difference. There were some awards for like best paper, some runner-up, most interesting new directions. So these are the ones that I found most interesting. Outstanding New Directions Paper Award for Uniform Convergence may be unable to explain generalization in deep learning. So this relates to our previous MLRG topic. A lot of people have been trying to use uniform convergence, and basically they show that this approach is not going to work. Yes, and so this was quite interesting. This paper was about putting an end-to-end training, and so you do local training at different parts of the network with a local objective function, maximizing mutual information. And then on the last one or two layers, they do some supervised learning to actually have it be able to make predictions for your loss function, your ultimate goal loss function. So it's interesting that this actually seems to work quite well. All right. Okay, so this is one of the talks by Celeste Kidd, How to Know. It's basically, it's about how we form beliefs and so it's relevant to life in general. There's cute videos and pictures. She experiments on babies because I think they're easier to do these experiments on than with adults. But presumably this applies to people of all ages. So babies preferentially focus on stuff that is moderately surprising. So if it's too surprising or it's totally boring, totally normal, they don't focus on that. Which you could see this being a good strategy to explore to improve your model of the world, right? So that you hopefully know enough to be able to tackle and understand this new thing, but you're not totally lost and unable to make progress. And secondly, certainty diminishes interest, regardless of whether we are actually correct. So once we become certain, we're not interested, and then it's very hard to correct our mistaken beliefs. I think this has actually come up in teaching physics. You have to, like, over and over again show students that their theories they made up are incorrect. And then they become open to learning how the world actually works. Yeah, so certainty closes our mind, and we become closed to future evidence. And I think this has blocked progress in certain fields for long periods of time. And yeah, our certainty is not a good predictor of whether we are actually correct. I think this quote sums it up. It's impossible for a man to learn what he thinks he already knows. So how do we become certain about often the wrong conclusion? Well, certainty forms from feedback. So we feel confident and certain when we get initial feedback telling us that we're correct. And this is possibly from a Google search. So you can see now the order in which the Google search results come up could lead to very different outcomes in terms of what people believe and become certain about. Here's an example of how the order in which information is presented becomes quite important. So activated charcoal, it's like a health fad. So participants would watch 3 YouTube videos, each 3 minutes long, on the health benefits of activated charcoal. Now the subsequent videos would confirm the theories they started to make in the first video, right? Leading them to become, they're getting feedback on their theories, leading them to become quite certain, oh yeah, this is the way the world is. Activated charcoal is a really healthy thing. And so then they become certain and close to future evidence, right? However, if countervailing perspectives are presented in the second video, right after the first video explains how awesome it is, they're much less likely to become certain and close to new information. So yeah, getting that countervailing perspective earlier or early is very important here. Another example from science, a theory is presented. Initial results and papers support the theory, and there's some spectacular examples of this. And so premature certainty about the theory is formed. And this can sometimes lead to decades of dead-end research. And because of, like in science, we've got this peer-reviewed approach, right? For grant funding, for papers being published. And so ultimately those who don't buy into what most people are certain of, their careers get destroyed. And yeah. And so I think the AI winter, like, I guess for a long period of time, it wasn't until there's some pretty definitive results that kind of the mainstream came back to, oh, neural networks do work. So my takeaway is that we need devil's advocates, and we need to hear them early on before we get some false certainty about something. All right, and that's that talk. Again, it's like a fascinating talk that's accessible to pretty much anybody. So the next talk is Social Intelligence by Blaise something or other. This is a fascinating talk about the high level of AI and AI research and some exciting future directions. So if you're interested in this topic, I highly recommend this. I don't think most of this is that useful today in practice, but it may shape our future significantly. So first of all, some things that are happening. We're having TPUs, edge TPUs, so basically a little GPU on your cell phone so that you can locally process things. Because most of the energy is actually used to send the data from wherever it's collected to the cloud somewhere to be processed and then sent back, right? So if we can start to do a lot of the processing locally, you could save a lot of energy and a lot of time, obviously. And then there's things like federated learning for somehow combining learning from all these different locations. But here's where it really starts to get interesting. So recently we've gotten quite good at using neural networks to optimize a loss function, right? Given sufficient data. But he says being able to optimize a loss function unfortunately takes very little ground in AI. How do you create a loss function for optimal hiring, for criminal sentencing, couples therapy, art? All these things that we as intelligent agents can do it's very hard for us to create a loss function in order to be able to train a neural network to be able to do this for us. And loss functions are not how evolution designed our intelligence, right? So, so he looks to evolution. In evolution, I mean, there's incentives, kind of rewards in terms of reproduction, but there's no single best solution, right? There's multiple solutions exist. And some stable points may exist, so things may converge, and those might look like optima. Technically, they aren't, though. But we can also, aside from stable points, we can have like rock, paper, scissors type dynamics, where given most of the populations here, it's better to evolve in this direction, which means, and then once you're here, it's better to evolve over to here, and so the genetics basically can go in a circle. Yeah, so evolution isn't about optimizing a reward function. It's a messy, dynamic process, right? It doesn't reach an optimum and stop. So one of my takeaways is like evolution is a very general learning approach, dynamic learning approach. And we can probably make a lot of progress in AI by using massive computational power to find messy processes that work, and then try to understand those processes. And I think this is similar to how neural networks became big. We had GPUs that could crunch bigger neural networks, and we got some really good results, and then we improved on them and improved on them, and now we're trying to understand why neural networks work, and we're making progress on that so that we can actually more systematically use them in an engineering sense. But it was initially like the computational power was what allowed us to make that breakthrough. Cool. So perhaps even more interesting than this is how he looks here at how we train neural networks and then generalizes that and takes an evolutionary approach. So this would be just a regular feed-forward neural network. So the output of the next layer is a weighted average of the outputs of the previous layer. Looks like he's missing the nonlinearities here. This is often all that we think of, right? Autograd takes care of everything else. But if we were to think of the autograd manually, in the backwards pass, the backward signal is also a weighted sum of the backward signal from one layer ahead, right? So this is kind of a local, it's a local rule for doing the back propagation. And then the weights would be changed something like this if we're just doing simple SGD. Of course, if we've got momentum or we've got atom, then we're going to have more equations than this, and it'll get a bit more complicated. But we can see there's signals forward and there's signals coming back, right? Well, maybe we can generalize this. We can think of them, if we had momentum, that would be some kind of internal memory for each weight. Yeah, so something maybe like an LSTM over the update steps. The LSTM could give you memory over time over your updates. And we could have different kind of momentums or different LSTMs with different time constants in that they could remember for shorter or longer periods of time. And that would be analogous to there's different processes like chemicals, electrical, that happen at different timescales in our brain as well, right? So we could generalize this, add in things like momentum, add in multiple timescales and not just a single momentum, and come up with some complicated update rule. And then we could learn the update rule. So here, this is based on derivatives, right? So instead of having it based on derivatives, let's just have evolution figure out what works well. So So what we're doing is evolving a more complex update rule than standard momentum or atom or whatnot. Maybe for specific parameter settings, atom might belong to this population of possible update rules, but we're exploring a much larger, more complex space of possible update rules. And then we train on MNIST with various sets of parameters, and then we select the sets that work better, and then we mutate them a bit, and then we train again. And so by natural selection on how well or how quickly we can train on MNIST images, we figure out the details of the update rules, the detailed parameter settings. Yeah, and so yeah, I'd point out again, here, these are vectorial. So instead of like having a single momentum, we've got multiple different momentums at once. And it performs incredibly well on MNIST. Now, as learning works, I guess, learning overfits to what it's been trained on. And so this algorithm has overfit to MNIST in that it's really good at training on MNIST. It's not as good on other things, but it does generalize and still performs better than these other training algorithms according to their graphs. Yeah. So this is big picture, getting away from simple optimization functions, I guess, and exploring the messy space of evolution and dynamic processes, and using lots of computational power. This next talk is also, I'd say, about the big picture of AI, but it's somewhat smaller and it's more focused on engineering. There's this book, Thinking Fast and Slow. You can watch the Google talk by one of the authors. And it talks about system 1 and system 2. So system 1 is your intuition. It's your recognition. You see an image, you know there's a dog in that image. How did you know there was a dog? You didn't look at it pixel by pixel and logically reason out it must be a dog. You just knew, right? So that's the parallel processing, and you just know. This is done in our subconscious, right? System 2 is more our conscious mind, and it's more that sequential, logical processing. So you think about something, if that, then this, and you've got just a few things in your working memory, and you're working with those one step at a time. So what neural networks have gotten really good at is doing system 1 tasks. Given tons of data, at least, neural networks can do system 1 type tasks very well. So how can we extend neural network capabilities to do more system 2 type tasks? That's what this talk talks about. And it looks like they've inspired by trying to create system 2 capabilities, they've actually got some useful innovations that are, getting good results. So, all right. So our training tends to be in the IID setting, right? But the world does not work that way. In the world, the rule is OOD, right? Not overdose, out of distribution. Agents always face OOD environments because they grow up, because new things or people come into their environment. The whole world changes, right? So how to do better on OOD tasks, on OOD transfer? Well, one approach, or one thing that helps, is compositionality. So the layers in neural networks help with OOD transfer because the low-level features can be reused to quickly learn some new high-level thing that has come into your environment. However, neural networks still fare very poorly compared to humans. in terms of OOD transfer. Of course, humans have been overfit to the world as it is by evolution, right? But cool. So one key thing that System 2 uses is attention. And his idea for how to implement this is to send the key as well. So we might have several things in our conscious mind that we're working with in our working memory, and we know what those things are as well, right? So the idea is to do attention, sending the key as well, and so now we have indirection. And we can use this. So the conscious mind you usually only have a few things in your working memory at a time. So whereas your unconscious does a vast amount of parallel processing, creating, so there's some inputs, a vast amount of parallel processing, which gives you some unconscious state. And then your attention picks out just a few things, and those things go into your conscious state. And then based on your conscious state, you can pick out new things from your unconscious state. And obviously what you get will depend on what's in your unconscious state as well. So there's top down and bottom up input here in terms of what new things are sent to the conscious state. And the conscious state, you hold things in mind for a while as you process, right? Maybe change some things, but things stay in the conscious state for a while. So which is why this is recurrent here, and he's modeling the unconscious similarly. Yeah, so you kind of have this feedback, and you can see with this architecture, you you're using kind of the same processing, but you can do multiple loops to figure stuff out, which will allow that kind of, maybe something like that conscious type of processing. All right, what do we have here? All right, so the consciousness prior. So the idea here is, so we only have a few things in our consciousness. And in fact, the way that humans tend to relate to the world is they see this and these things, and they're like, okay, this caused this, or these two things caused that, right? The real world generally is very complex, right? Lots of things can interact in some complicated causal manner to cause what's occurring, right? But we don't tend to focus on that. We just tend to focus on a few things, and I guess for a lot of what matters in the world, this captures enough of what's going on. So yeah, a sparse causal factor graph is kind of innate to how humans process information and understand the world. Yeah. So this is a nice example, I think. If I let go of the ball, it will fall and hit the ground, right? So there's a bunch of high-level concepts here, right? We're not talking about pixels directly. We've somehow made these abstractions, but there's very few of those abstractions in this single statement, right? Yeah. Cool. And maybe one of the most exciting things is they've gotten some good results. It looks like this would be expensive because of the multiple loops, but it works. It improves the results. So this seems to be based on this paper. You can see Yoshua Benjo is here. Also, Sergey Levin is here, right? There's some big names in this. You might be interested in reading this. I don't fully understand what's going on here. They've got some no passing gradients. Not sure what's going on there. You can see the key value attention that we talked about earlier. And you can see time steps. So it looks like it's using the same network repeatedly at different time steps. Sorry. Yeah. Okay. So, and that completes the general interest NeurIPS presentation. Thank you for watching.